We live in an era on the cusp of a technological revolution fueled by artificial intelligence. At the heart of this revolution lie neural networks, powerful algorithms mimicking the human brain. These networks are transforming industries and redefining machine capabilities. From self-driving cars to personalized medicine, neural networks are reshaping our lives. This essay explores their profound impact and potential to shape the future. At their core, neural networks are sophisticated computer programs inspired by the structure and function of the human brain. Just as our brain consists of billions of interconnected neurons, neural networks are composed of interconnected nodes or artificial neurons organized in layers. These artificial neurons, much like their biological counterparts, receive information, process it, and pass it on to other neurons in the network. This interconnected structure allows neural networks to learn complex patterns and relationships from data, mimicking the human brain's ability to learn from experience. Imagine a child learning to identify a cat. Each time the child sees a cat, their brain processes the visual information such as the shape, size, and color of the animal. Over time, the child's brain learns to associate these features with the concept of a cat, allowing them to recognize cats in different environments and poses. Neural networks learn in a similar way. By processing vast amounts of data, they identify patterns and correlations, gradually adjusting their internal parameters to improve their accuracy. This ability to learn from data without explicit programming is what makes neural networks so powerful and adaptable. To understand how neural networks learn, it's essential to grasp their underlying structure. A typical neural network consists of three main types of layers: the input layer, hidden layers, and output layer. The input layer acts as the entry point for data into the network. Each node in the input layer represents a specific feature or input variable. For example, in an image recognition network, each input node might represent the pixel value of an image. The hidden layers lie between the input and output layers, and are responsible for processing the information received from the input layer. Each hidden layer consists of multiple nodes, each performing a simple mathematical operation on the input it receives. These layers are called hidden because their inner workings are not directly observable. The output layer produces the final output of the network, which could be a prediction, classification, or a decision. The number of nodes in the output layer depends on the specific task the network is designed to perform. Think of a neural network like a factory assembly line. The input layer is like the raw materials entering the factory. The hidden layers represent the various processing stages where the materials are transformed and assembled. Finally, the output layer is like the finished product leaving the factory. The learning process in neural networks involves adjusting the connections between neurons, known as weights, to improve the network's accuracy. This adjustment process occurs through a mechanism called backpropagation, which works in conjunction with a process called forward propagation. Forward propagation is the initial step where data is fed into the input layer and propagates through the network, layer by layer, until it reaches the output layer. Each neuron in the network processes the input it receives and passes the result to the next layer until the network produces an output. Backpropagation involves comparing the network's output to the desired output and calculating the error. This error is then propagated back through the network, adjusting the weights of the connections between neurons to minimize the error in future predictions. Imagine a basketball player practicing free throws. Each throw represents a forward propagation, and the result, making or missing the basket, represents the network's output. The player then analyzes their technique, adjusting their posture, grip, and release based on the outcome of each throw. This feedback and adjustment process is analogous to backpropagation. Through repeated cycles of forward propagation and backpropagation, neural networks gradually refine their weights, improving their ability to perform the desired task. This iterative learning process allows neural networks to adapt to new data and improve their performance over time. Section 5. From Pixels to Predictions: Neural Networks and Image Recognition. One of the most well-known applications of neural networks is in the field of image recognition. From unlocking your smartphone with facial recognition to self-driving cars navigating complex environments, image recognition is revolutionizing various aspects of our lives. Neural networks excel at image recognition tasks due to their ability to learn hierarchical representations of visual data. In simpler terms, they can identify patterns and features at different levels of abstraction, from simple edges and corners to complex objects and scenes. Consider a neural network trained to recognize different dog breeds. The initial layers of the network might learn to detect basic features like edges, lines, and textures. As information flows through the network, subsequent layers might identify more complex features like ears, tails, and snouts. Finally, the output layer would classify the image based on the combination of features detected, recognizing the specific breed of dog. This hierarchical feature learning allows neural networks to achieve remarkable accuracy in image recognition tasks, often surpassing human-level performance in certain domains. Section 6. Beyond recognition neural networks in natural language processing. Another fascinating application of neural networks lies in the realm of natural language processing, or NLP. NLP focuses on enabling computers to understand, interpret, and generate human language, bridging the gap between humans and machines. Neural networks have made significant strides in NLP, powering applications like machine translation, sentiment analysis, and chatbots. By learning the intricate patterns and nuances of human language, neural networks can translate languages with impressive accuracy, understand the sentiment behind text, and even engage in human-like conversations. Imagine using a language translation app to communicate with someone who speaks a different language. As you type or speak, a neural network processes your input, analyzes the context, and translates it into the target language in real time. This seamless translation experience is made possible by neural networks' ability to learn the complexities of human language. From analyzing customer reviews to generating realistic dialogue for virtual assistants, neural networks are transforming the way we interact with language and information. Section 7. The roadblocks on the path to artificial intelligence. Despite their remarkable capabilities, neural networks are not without limitations. One of the primary challenges lies in their reliance on vast amounts of labeled data for training. Collecting, labeling, and cleaning such datasets can be time-consuming, expensive, and prone to bias. Moreover, neural networks often struggle to generalize their knowledge to new and unseen situations. They excel at tasks they have been specifically trained on, but may falter when faced with unfamiliar data or scenarios. Another challenge lies in the black box nature of neural networks. While we can observe their input and output, understanding the internal decision-making process of a complex neural network can be challenging. This lack of transparency can make it difficult to diagnose errors, identify biases, and ensure fairness in their predictions. Addressing these challenges is crucial for unlocking the full potential of neural networks and building trustworthy AI systems. Researchers are actively developing techniques to improve data efficiency, enhance generalization abilities, and enhance the explainability of neural networks. Section 8. A future shaped by neural networks. Despite these challenges, the future of neural networks is bright. As research and development in AI continue to advance, we can expect to see even more innovative applications of neural networks in various domains. From personalized medicine, where neural networks can analyze medical images and patient data to assist doctors in diagnosis and treatment, to drug discovery, where they can accelerate the process of identifying potential drug candidates. The potential applications of neural networks are vast and transformative. Neural networks are also playing a crucial role in addressing some of the world's most pressing challenges. From climate modeling and environmental monitoring to disaster prediction and resource management, these thinking machines have the potential to drive positive change and create a more sustainable future. As neural networks continue to evolve, they will undoubtedly reshape industries, transform societies, and redefine our relationship with technology. Section 9. Conclusion: the dawn of a new era. Neural networks represent a paradigm shift in artificial intelligence, enabling machines to learn and perform tasks that were once considered the exclusive domain of humans. From image recognition and natural language processing to self-driving cars and personalized medicine, neural networks are rapidly transforming various aspects of our lives. While challenges remain, in terms of data efficiency, generalization, and explainability, the future of neural networks is full of promise. As research and development in AI continue to advance, we can expect to see even more innovative and impactful applications of these thinking machines. The rise of neural networks marks the dawn of a new era, an era where machines can learn, adapt, and work alongside humans to solve complex problems and create a better future. Embracing the potential of neural networks while addressing their limitations will be key to harnessing their transformative power and shaping a future where AI benefits all of humanity.